solve here for sine x dx, that's minus du, and then this becomes u cubed. This works, this type of substitution works with sine and cosine integrals as long as at least one of sine or cosine is present to an odd power. If everything is even, like in problem like this one, then you have to use trig identities, which we'll do. But as long as you notice in this problem that both sine and cosine are there with an odd exponent. You could have that, or you could have a case where, for example, this could be an even exponent as long as you have the sine there with an odd exponent. Or you could have the sine with an even exponent as long as you had cosine with an odd exponent. When we look here at problem 11, you'll see a little more what I'm getting at. But anyway, to finish number 3, which is, of course, comparatively easy, calling this u and identifying sine x dx with negative du, we have u cubed minus du, and so the minus comes out, and you have u cubed du's, so we have u fourth over 4, and then you substitute back. And don't forget to put on the plus constant. It's an indefinite integral. Now, in this one, again, both exponents are odd. That wouldn't matter as long as one of them's odd. You'd still do the kind of thing that I have done here. So what I do, you see, where there's a factor with an odd exponent, is I slice out a sine or a cosine, whichever the case might be, to the first power. So that, together with the dx, is going to be my du. So if cosine x dx is du, then the u would have been sine. Because if u were sine x, the du would be cosine x dx. So this becomes then u cubed in a minute, and out of cosine cubed, having taken the one cosine with the dx to make my du, I have a cosine square. So now I have to use trig identities to connect the cosine square with the sines over here. Remember, the sine is going to be the u in a minute. So now I have sine cubed, cosine square, which is 1 minus sine square, which is why you took trigs somewhere at some time. And then I have the remaining cosine with the dx. So if this is u, I get u cubed. Then I get 1 minus u square, and then this part makes the du. What you want to do in these problems where you're using trig identities and using one of the trig functions as the u is rewrite the problem using powers of u as quickly as you can. It's easier to do algebra with a letter raised to a power than it is with the name of the trig function. You just trip over your shoelaces a little bit when you're writing the names of the trig function. So finally, you've remade the problem as u cubed 1 minus u squared du, which is now a totally algebraic type manipulation. So multiply these together, you have u cubed minus u fifth. So now you add 1 and divide by the new exponent, and you get what I have here. And then remember, you have to substitute back to the original letter, because the meaning of writing something with functions of x and then the dx over here is that you will write the answer using this variable. So it isn't really correct to stop here with the 1/4 u4 minus 1/6 u6. You either have, if you're doing an indefinite integral, you have to go back to the original variable. Of course, if you had a definite integral, you would have changed your limits, and then you'd use your new limits here, and you'd get a number. So the procedure here works with sine and cosine products as long as one or the other, at least, is an odd exponent, so that you can either slice out a cosine to make the du or a sine. You could have done this the other way. You see, you could have let u be the cosine, and then this one of the sines with the dx would be minus du. You could do it that way too, and it'll work all right. And what you'd have is an answer down here in terms of cosines instead of in terms of sines. And that's all right, because they're always related, aren't they? Sine squared plus cosine squared is 1. So this is not the only way that the answer could be given. It could be with cosines and cosines, and then it would be a different, you'd say plus c, but the constant would be a different number, actually. Now, if you're looking at something like 13 and 14, you see you have even exponent only. So now you can't play this game. So what you do is trig identities. You can reduce the exponent. For example, if you look at 13 where you have cosine square, you can reduce the exponent by 1 if you will pay the price of going from square with a letter as your angle to either cosine or sine, as the case may be, with the angle doubled. So a reduction in power is something you can purchase, and the price you pay is you have to double the angle. So the identities then that are going to apply here are, first of all, cosine of twice an angle is cosine square minus sine square in the trig class. And then if you replace sine square with 1 minus cosine square and do your algebra, the two minuses here make a plus, so you get 2 of these minus 1. And so you can solve for 2 cosine square by adding 1 to both sides. So you reduce the exponent from 2 down to first power, and the price you pay is you double the angle. And if you want cosine square alone, you can divide by the 2. You can also do the same thing with sine square, because again, your cosine of twice the angle, if it's cosine square minus sine square, you can replace the cosine square with 1 minus sine square, and then you have this one. So now you have 2 of the sine squares, and then you solve for that. So 2 sine square is 1 minus cosine 2t. Again, what you're buying is reducing the exponent, and what you're paying is you're doubling the angle. And these are whichever way you want to say it in the trig class, half angle formulas or double angle formulas. That depends on which way you're looking. Notice that with the sine square formula, there's an I in sine and there's an I in minus. And with the cosine, there's no I in cos and there's no I in plus. That's how I remember it. You can remember it any way you want it. But you use these if you have only even powers, because you can make the substitution and cut the exponent down. And so, for example, if you're doing cosine square, you can go here and bring the 2 across, and you have this identity. Then you integrate 1/2, that'll give you x over 2, and you integrate the cosine of 2x, which would be sine, and then you have to divide by the frequency. And you also have this 2, so you have the 2 times 2 here. So then, if you simplify this, you have an answer of this sort. So I have a recipe box over here. If you have either cosine of ax or sine of ax, then you divide by the frequency. Remember, frequency is the name for what multiplies the variable in sine or cosine. So you have these for your antiderivatives. You would prove these formulas really using a u substitution. You see, u would be ax, and then du would be a dx, so the dx would be du over a, and that's where you get the a in the denominator. But it's too much time wasted to keep doing and redoing u substitution, just to try and learn a few of these things. You have the same sort of thing with secant and tangent. So, meanwhile, look at problem 14, which is similar to 13. You have sine squared this time, and you notice it's a definite integral. So, with your sine square, you can replace the sine square with the double angle and cut your exponent from square down to first power. So that's what I've done here. And then I can integrate the half to get x over 2. And then I have the half, and then sine 2x using the recipe right here over 2. So I'll have sine 2x over 4. Now I go 0 to pi over 2. So I have pi over 2 over 2. And then here I have 2 times pi over 2, which is pi at the upper limit. At the lower limit, everything is 0, isn't it? I put 0 there, and sine of 0 is 0, so I didn't bother to write it. Okay, and sine of pi is 0, so what you really have is just right here, the pi over 2 over 2. Okay, so any questions so far? We've done 4 of these. Anybody have any question on this? This is not really that hard to do, I think. However, these next secant tangent problems are a good deal more involved. 33 isn't, but 34 is, as you can see. So if you look at 33, you have secant square tangent, and if you think of u as tangent, so I put a u there, the du, the derivative of the tangent is the secant square, so your du becomes secant square dx. So then this becomes u replacing the tangent, du replacing the secant square dx. So then what you want is 1/2 u square, which somehow didn't get written. However, I did write tangent square, so I eventually got there. Okay, that looks better probably. And then you substitute, you have the 1/2 tangent square. Okay, now here you see things can become a good deal more complicated. So if you look at number 34, you have tangent square secant. And so what you can do is trig identity, tangent square becomes secant square minus 1, and then this secant is over here. So now you have secant cubed minus the secant times here, the integral of secant. So the question is, how do you do those integrals? And this one we will integrate by parts, which was yesterday's class. And this one we do with some trickery, as you will see. If you were reading the book, I think they do secant cubed in the book as an example, but I have it here on the board. And I think they also show you the trick for this, which I will do on the board. So the game with secant cubed is let the u be secant, and then du would be secant tangent. And if you've sliced the secant out of here for the u, then the dv has to be everything else from yesterday's class, right? So that leaves secant square and dx. And you see, in your selection for what you're going to call dv, you have to choose something where you can do the antiderivative. You have to be able to get v in order to use your integration by parts formula from yesterday. Remember, the integral of u dv is uv minus the integral of v du. So you have to know the v. So if you take your dv here as secant square, you can get v because derivative of tangent is secant square. So that's what's prompting me to split this as secant and secant square. There isn't much else you could do after all. It's not going to do you any good really to take the secant cube as your dx as your dv, because that's the problem you have. So it's about the only game that you could hope to play, really. So now I have my secant cubed is my uv, okay, my u is secant, and my v is tangent, minus the integral of v, which is tangent du, which is secant tangent. So this tangent and that one together make the tangent square there, and then the secant that's here is this secant. So this is my uv minus the integral of v du. So then the question is, what do you do with this? And so, like we were doing yesterday with some of these integrating by parts things, we integrate by parts again and get an equation that we solve. So we're doing this very much the same way that yesterday we did the e to the theta sine theta and e to the theta cosine theta type problems, where we did integration by parts twice, and finally we had an equation. If you were here yesterday, you should remember it was over in that part of the board. We had e to the theta, say cosine theta, and then we had two terms, and then minus the same integral again, e to the theta cosine theta, and then you took the integral across, solved like an algebra problem. So it was a mix of calculus and algebra. So that's what we're on our way to doing here also. I pointed this out here, that notice that we solve secant cubed integral reasoning with a mix of calculus and algebra in the same way that yesterday we solved e to the theta sine theta and e to the theta cosine theta by doing integration by parts twice and then getting an equation where the integral we wanted was on both sides of the equation, and then we could solve for it as an algebra problem. So that's what we're in the process of doing. What we have so far is that the integral of secant cubed is secant tangent minus this integral, and then we'll do integrating by parts again with the new colors, and we'll finally get secant, integral of secant cubed equals a couple of terms, and then we'll have minus the integral of secant cubed over on the right. So we have the integral of secant cubed is secant tangent minus what I've done now, you see, is I've replaced tangent square by the identity secant square minus 1. So putting secant square minus 1 in here gives me secant times secant square, which is this integral, and secant times minus 1, which is this integral. And you're following the minus sign, so the minus is there, and then that makes that one plus. So I have an equation that the integral of secant cubed is secant tangent minus this same integral again, plus the integral secant. So I can take this across the equal sign, that makes it plus, so there are two of them. So 2 times the integral of secant cubed is secant tangent minus, or no, plus rather, this plus, the integral of secant. So we can do the integral of secant cubed now as an algebra problem if we can get this. Okay? So we can do the integral of secant. That's in the book, and I'll show you. You use a trick. Secant certainly equals itself, times 1, but you write 1 in a tricky way. You have secant plus tangent on top and tangent plus secant on the bottom. But it is, after all, the same thing. A plus B equals B plus A. The reason I do it this way is that then if I multiply this secant times those with the distributive law, I have secant square and secant tangent on top and tangent plus secant on the bottom, which I'm calling U. If I call that U, this is exactly the du. You see, the reason I wrote this in the reverse order compared to up here is that for each term here, its derivative is right above it. The derivative of tangent is secant square. The derivative of secant is secant tangent. So if this is u, this times dx is du. So I have the form du over u, which of course is log, as long as this is positive. And so to be sure that it is, you write log absolute value. So this is the formula that you find in the book. They work it out as an example, and then you can find it in the table in the back of the book for the integral of secant. Log secant plus tangent plus constant. And then what you do is you go back to here, where we have 2 times the integral of secant cubed is secant tangent plus this integral, which now we know is log secant plus tangent. So we did integrate by parts to do the secant cubed, but we also got to a place where our integration by parts gave us the integral we want equal to a product minus this same integral we want plus another integral. And so we also did algebra because we took this across to get 2 of them. So in that sense, it's a little like what we did yesterday with the e to the theta sine theta. So what we have here now is that 2 integral secant cubed is secant tangent plus this, which was our integral of secant. And so secant cubed itself is half of secant tangent plus log secant plus tangent plus constant. And so we're still trying to do problem 34, which you see from the first time around with integrating by from doing trig identities is equal to this integral, which we've just solved up here, minus this integral, which we have solved down here. So you have problem 34 as the difference of 2 integrals now that you know. And it's this integral minus this one. Okay, so this integral then from up here is the 1/2 secant tangent plus 1/2 log, and rather than writing it as log, I wrote it as the integral of secant, and then I'm taking away the integral of secant. So I have the purple plus 1/2 integral of secant minus integral of secant. So it's this these two make minus a half integral of secant. And then I replace integral of secant with what it equals. And I factored the half out in front. So I have secant tangent from here, and then the integral of secant, which is this log from there. So finally, we get to our answer, which is a half secant tangent minus log absolute value plus constant. So that's quite involved, really. But you notice that in the process of doing it, we've learned how to do the integral of secant cubed, and we've also learned the tricky form for integral of secant. You can do similar things with cosecant cubed and the integral of cosecant, which it's the same sort of stuff. However, they're not used that much. Okay. So notice then that problem 34 that we're just working with is really three problems at once. It involves getting the integral of secant, which we've done by parts, the integral of, integral of secant cubed, which we've done by parts, the integral of secant, which we've done by trickery, and then what the question asked, which was this one, which was actually, as we see here, the difference between these two integrals. Okay. So we also have, let's see, better do this before I forget.
Thank you.
Okay, so then the other thing that we have here at the end of the section is some factoring formulas, which allows us to do products of that look like 51 and 52 here. So if you remember what factoring does, it converts a sum or difference into a product or a quotient. And the things you multiply together are what you call factors. Expressions that you connect with plus and minus are what you call terms in algebra. So factoring is converting a sum or difference of terms into a product of factors. So we have three factoring formulas among our trig identities. And you see, for example, here you have a difference of cosines, and you convert that into a product of sines with this formula. You have a sum of sines, and you convert that into a product of sine and cosine. Or you have a sum of cosines, which you can convert into a product of cosines. So these are in the book, and we're basically taking the author's word for it because this is not the trig class. And so you use one or the other of these factoring formulas for problems that look like either 51 or 52. People also call these things sum to product formulas because that's another way to say what you have. You have a sum of terms here, and you're converting it into a product. Okay. So, for instance, if you were looking at 51, where you have sine of 3x, cosine of 2x, then the m in the recipe here is the 3, and the n in the general recipe here is the 2. So you have the sine cosine type situation. So it's the center one where the m is 3 and where the n is 2. So taking this recipe, you have the 1/2, then you have the sine of m, which is 3, minus n, which is 2. And then you have the sine of m plus n, which is 3 plus 2. And so you have that in here. Okay, 3 minus 2 gives you x, and 3 plus 2 gives you 5x. And then your integral of sine is negative cosine. Your integral of sine 5x is negative cosine 5x over 5. See, I'm back to my recipe box here. And so then you leave your answer like that. With 52, you have much the same idea. Again, this would be your m, and that would be your n, and you have sine cosine. This time, if your m is 2 and your n is 3, you have sine of 2 minus 3, so you have sine of minus x. And then with the 2 plus 3, you have sine of 5x. So remember that the sine is an odd function. Sine of minus x is minus the sine of x. And so you can replace this way. And the cosine is even, not that I have a cosine here, but if you did have, it would just be the same as cosine x. Okay, so then my integral of minus the sine will be cosine, and my integral here will be minus cosine 5x over 5, and then I have the half out here. And so you could call this one half cosine x minus cosine 5x over 10 if you want. Well, this is pretty well what's in the section. What we will do next week that we would start with are harder problems than these. We often have, let me give you just a kind of a preview very briefly. We often have problems of one of these 3 types. So when you get any of the 3 situations, which we will find in the next section, where you have either a sum or a difference of squares, you notice that with the sum of squares, this would be the same thing as if you wrote u squared plus a squared, so it wouldn't make any difference. Here, the order matters, you see. It's variable minus constant or constant minus variable. So what you can do with all three of these is to use trig identities, and what you gain from the trig identity is you can write either your sum or your difference of squares as a single term. And I'll show you this in just a second. That's a perfect square. So then you'd have the square root of a square, and you can get rid of the square root sign. The price you pay is you then have to do your integral working with the trig functions. And then when you get all finished, you have to get back to the original variable, or else you have to change your limits as with any substitution. So if you have this type, you could do this. You could do either sine or cosine, and then you'd have a square plus u square becoming I guess that's the wrong one. When it's plus, you want tangent. So then you'd have so what you take advantage of is that 1 plus tangent square is secant square. So you get a square secant square t. So if you do this and you have made the substitution here, you have this under the square root, and then this one, and this one. And so as long as you're working in the first quadrant, your trig functions are all positive, so you don't have to worry about absolute value on the square root, and you can say a secant. So what you gained is you removed the square root from your integration, and the price you're paying now is you have to integrate the secant, which you notice we just finished learning how to do with our trick right here. And so this is our integral in secant. So this is one reason why I went through this, because if you notice how these calculus books are made, often what you do in section 3 is exactly what you need for section 4. It's a just-in-time type of manufacturing sort of thing, the way the Toyota company makes its cars and so on. And so it's the same sort of thing. So you do this with this one, and then if you have this one, this is the one where I either want to use sine or cosine. It doesn't matter. So if you do that, then you're going to have, wait a minute. Now I guess that one's down here. This one you want, let's see. Now, this one you want secant also. So your secant square minus 1 is your tangent square, which we were using over here also, right here. So that will make this a square tangent square. And then you can take the square root of that. And again, if you're in the first quadrant, your tangent's positive, so you don't get tangled up with absolute values. And so you're working with a tangent t. And then finally, this one will be sine and cosine. I've been stumbling over that. If you let u be, for example, a sine t, then you'll have and then you can factor the a square, and you have and then that's a square cosine square. Like that. So you see, you can handle all three of the cases where you have either the sum or the difference of squares under a square root or a square root raised to any power, and you can get rid of the radical by going to trig functions. And so that's what the next section is about. That's what we'll take up on Thursday of next week as a way of preview. And you notice that we do work with the secant and get the integral of secant, which is one reason, as I said, why I went through doing the integral of secant today. So if you did not give me your test yesterday, I trust that it's here or that you're about to turn this in. And so I wish you a good week, and we'll see you